And I'm not going to go through these, but maybe we'll talk about them in a couple example cases. So first, if you consider the strategy that Shai and I used, so that strategy was to use the first card to designate the suit, and then use the remaining cards to designate how much to this card you were supposed to add to get the hidden card. So these are permuted to tell us how much to add to this card. The question is, what size deck could this possibly work for? And for the case when we choose 5 cards, the case that this does work for, or that this strategy is suited for, is for a 52 card deck. So if our let's see, let's let n be the number of cards we're choosing. And let d be the size of the deck. Okay, so if n is 5, then the number of suits we can have is 4 suits, because we need to apply the pigeonhole principle to allow the pigeonhole principle to work, so that we get 2 cards of the same suit. So we can have 4 suits, and then the remaining 3 cards. So I guess this is in general n minus 2 cards. So the remaining 3 cards can be permuted. There's 3 factorial permutations of that. So but we had a choice as to which card we chose from the given suit, and so the actual total number of cards that we can have in the deck is 2 times 6 plus 1. So the total number in the suit is 2 times 6 plus 1, which is 13. And so the total number of cards in the deck for which this strategy works is 4 times 13, which is 52. So I guess what the one question is asking you to do is to make a similar argument for supposing you chose, well, n cards. What size deck could you possibly get? Does this make sense so far? Okay. So the next question that is on the problem set asks you about how to, what's the maximal total size deck that this could potentially work for. I mean, it may or may not work, and you have to figure out how big that deck could be. And I'll leave that for you because it's sort of a fun counting exercise. But what I really want to talk about today is, well, if we have some deck size that's not bigger than the upper bound, how is it possible to find a strategy, or how many strategies are there, so on and so forth. So given a deck of size d, which is less than or equal to the lower bound, or the upper bound rather, is there a strategy that works? And I guess in theory, you could just ask your computer, check all the strategies. Is that going to be very efficient? How many strategies are there? So, So how many strategies are there? Well, we have a deck of size D, and we're choosing n cards out of it. So there D choose n possibilities we have to account for. Think of these as n choose D digits, if you will. N choose D possible answers that we have to find. And how many, when we have a particular subset of size n, how many possible things could we choose to show? So if we have, given a subset, right, so given a subset of size n, how many n minus 1 cards can we show? So we have to choose the n minus 1 cards, and then there's n minus 1 permutations. So it's n choose n minus 1 times, well, times n minus 1 factorial. That's the number of permutations of n minus 1 cards. Shai is now hidden in the audience. This works out to be n factorial.
I'm impressed with how the blackboard has really gotten worked in over the last couple months.
Has gotten what?
Like you can really see the chalk on the blackboard. The first couple weeks it was trouble. I know what you're thinking. You're thinking, what is he talking about? It is better, isn't it better? The blackboard's working better. What was your question?
It still isn't.
Oh yeah, well that's because there's a secret passage behind it. At least in the bathroom.
Right.
So that explains something.
Okay, so given a subset of n cards, there's n factorial possible things that we can show to the magician. And so how many possible strategies?
And your phony proof was that you left out the n choose n minus 1 when you first explained this problem, right? And then you said, oh, there's only 24 different ways, so it's impossible. And remember?
Right.
Tara made a phony proof at the beginning that you couldn't do this puzzle because when she gives me the 4 ordered cards, she can only give me 24 pieces of information, and that's not enough to get the other 48 cards that are missing. And that's because she left out the n choose n minus 1, that she had a choice to take those 4 cards out of 5. So it's really 120 different things that she could have told him.
So in theory, we could do that trick with a 120 card deck, 124 card deck.
4 card deck. That's the method.
But yeah. Okay, so if we have these for each possibility, we have n factorial choices. That means that the total number of strategies, and probably a lot of these are going to be awful and just not work. Well, is that in each position, in each of the d choose n possibilities, we have n factorial possibilities. So it's n factorial times n factorial times n factorial d choose n times. Does that make sense? Does everyone believe me? So that's really big. I wouldn't want to make my computer run an algorithm for n very much bigger than 4, I guess. With what? Not even? Yeah, I mean, I guess.
3 cards and a deck of 8.
Okay, so if I don't want to erase any of this.
Yeah, so
If d is equal to 8 cards and we're choosing 3, then n factorial to the 8 choose 3. Well, 3 factorial. 6 to the 8 choose 3. Is what?
Choose 3.
36.
56, right? 6 to the 56. So 2 to the 56.
Yeah, so it's big. So even checking all the possible strategies for choosing 3 cards from an 8-card deck is not very efficient. And so in particular, I mean, you really wouldn't want to check all the strategies for choosing 5 cards out of a 124-card deck. I mean, that just seems like not the best way of going about this problem.
What is 6 to the 56? Is it?
I don't have a calculator.
What's 60 to the 56, say, divided by 1 billion? Let's say you could do 1 billion of these in a second.
God, all these Palm Pilots.
Can we do that? Does anybody have something we can calculate there?
7 to 34th.
7 to the 34th. So take out 1 billion, takes off how many zeros? 9 zeros. So take off 9 zeros, you get...
No, I already divided it out.
This is already divided by 1 billion?
That's divided by 1 billion? Oh.
Yeah, that's what I got.
No, to the 25th. 10 to the 25th.
25th. Okay, so 10
Okay,
to the
so
25th. How many years is 3.7 times 10 to the 25th second?
I can do that too.
Is it centuries?
From seconds to years.
Oh, cool.
That's 1.2 times 10 to the 18th years.
But this is really important. I mean, I want you guys to realize just how ridiculously intractable this problem is. That's if a computer can do 1 billion of these in a second. So, okay, so just wait a couple of years because everybody knows they're getting faster, right? So let's make them 1 billion times faster, and then we get it down to
10 to the 9 years.
10 to the 9th years.
1 billion years.
Right.
That's practical. That's practical.
Could we analyze it in terms of growth rate of speed, like using Moore's law or whatever, and see how long it would take?
See how many centuries it would take until computers were fast enough for us to actually... Well, let's imagine this. Let's say you could do an operation in the time it took light to move a micron. I mean, I don't because I think that idea of how fast computers is going to improve has some limits as well, right? I mean, it works for the next 30 years, but
yeah, Moore's law is kind of a commercial concept. But if you say that, okay, perhaps the speed has an absolute limit, maybe there isn't much of a limit to the number of computers you could have working in parallel, or the rate at which you could produce the actual hardware.
okay, so let's say we'll have a computer on every atom in the universe. No, I'm serious. Every atom in the universe will have a computer, and they'll all work simultaneously. It would be hard to parallelize this computation, of course, we realize, right? Because this computation
Has to check.
look at everything that was done before. So the issue of parallelizing it is just completely hard. But let's just assume by some miracle we could parallelize it perfectly, and every atom had a computer. How many atoms are there in the universe? Does anybody have a ballpark? 10 to the what? I don't know.
But how, if every atom has a computer, then what about the computers that are on atoms? The atoms that are in computers, do they also have computers?
I just want to know. I know. So every molecule has got a computer.
Big number.
Right.
That's what the universe is.
Just finding a strategy for 3 cards out of 8.
When the universe ends, there's going to be one big explosion and the 2 of spades will show up. That's your card, everything else is a detail, right?
Okay, so whatever, I don't have anything else to say today. I mean, I'm done. So let's try and find a strategy for 7 choose 3. Let's just sort of see if we can plow ahead and get stuck or not get stuck or what.
And your strategy won't work for this, right?
My strategy. So here we have 7 cards in our deck.
Should we try to see where your strategy would mess up? Like what it would...
So let's suppose that we have 7 cards. Well, that's the question. First, we have to figure out how many suits we want to divide them into. Okay, so we have a 7-card deck. We want to choose 3 cards.
Right. So now you get to answer your own question. If you're choosing 3 cards, how many suits can you have to guarantee that you're going to have 2 of those cards be the same suit? 2. Right. Right, 2 suits, right?
Okay, so there's 2 suits. I don't know, let's call the low suit and the high suit. 1, 2, 3, and 4, 5, 6, 7, or 1, 2, 3, 4. Okay. So now we guarantee that we get 2 cards in the same suit. I guess the problem is, so first we want to put the suit here. We have 1 card hidden. And we have 1 more card that can tell us how high to go.
So that tells us 1, right? That doesn't tell us anything except 1 all the time.
And so that's not going to work. I mean, there's just no way. If we get, well, so the point is, if we have, suppose we have 1 and 3 and 4 and 7, or 1 and 3 and 7 that we chose. Oops, no, I guess it works for that. It works for, so suppose we have 4 and 6 and 2 that we chose. Okay, so 4 and 6 are both in the high suit, but, well, so suppose I want to show 4 and hide 6. Well, showing the 2 here is going to say 1, so that's supposed to signify that 5 is hidden, not that 6 is hidden. And similarly, if we put the 6 here, the 6 would signify that, or the 2 would signify that 7 was hidden, not that 6 was hidden.
Right, so in particular, your strategy for 4, 6, 2 and for 4, 5, 6 will be the same, right?
Right.
Let's write those down, because I want people to realize what makes a strategy bad.
Oh, right. Right, so here if we had 4, 6, 2, 4, 6, and 2, 4, 5, in both of these cases, we would have to put the 4 here and show the 2.
So if I'm doing this trick with tower and I see 4, 2, I don't have any clue whether it's a 6 or a 5.
Right, so we
That's
can't.
when strategies are bad.
So yeah, so a strategy is bad if we have for two distinct sets of 3, we have the same set of 2 that we're showing. Okay, so strategy is bad if for 2 subsets of n, you generate the same, for 2 distinct subsets of n, you generate the same n minus 1 subset. And so if you're going through your dictionary to figure out which card is hidden, you can't figure it out because there's 2 possibilities.
And for the case of 3 cards chosen, once you're 9 or higher in the deck, any strategy will be bad. Right? Once you have, if you're choosing 3 cards and you have a deck of 9 or more, then any strategy you choose by definition will be bad because you just don't have enough of these ordered 2 pairs to go around. That's how you get the upper bound to begin with.
Right, so maybe we should write that down. So suppose n is 3. And we want to figure out how big of a deck how big of a deck will not admit a strategy. So if we have 9 cards, if the deck is size 9, so this is what Shai claims, If we have a deck of size 9, then we can't possibly make any strategy work. So if we have a deck of size 9, there's 9 choose 3 possible 3 subsets. So 9 choose 3 possible things that we could be thrown. What's 9 choose 3? 9 times 8 times 84. Good. And there's the possible things that we can encode. That's the possible ordered pairs of cards from a 9-element set. So that's 9 times 8. So this is possible 3-card subsets, and 9 times 8, which is 72, is the possible number of ordered pairs.
So by the pigeonhole
But now by the pigeonhole principle, at least 2 of these are going to show up for the same guy over here, which means that it's a bad strategy, or that any strategy would be a bad strategy. So does that make sense? You can make a similar argument for, I mean, this is sort of how you can find your upper bound for any size n for your deck size. So you have to figure out for which size of the deck is the number of n card subsets bigger than the number of n minus 1 ordered subsets. Okay, so 9 is too big. A deck of 9 is too big, but a deck of 7, I claim, isn't too big. If we compare 7 choose 3 to 7 times 6, well, 7 choose 3 is bigger than 7 times 6. So, whoops, no, the other way around. 7 times 6 is bigger than 7 choose 3, so 7 cards work. So let's, and we know that our original strategy didn't work for 7 cards, so let's just sort of brute force try and write down a strategy that we think is going to work. So what I have to do is for each, I've carefully beforehand written down all my 3-card subsets. So now we have to figure out which ordered pair we're going to associate to the hidden 3rd card for each 3-card subset. I mean, essentially what we have to do is write down a dictionary that, I get handed a 3-card subset, I look it up in my dictionary, and then I put 2 of them down, and then Shai picks up his dictionary, and he goes through and looks at the 2 cards and finds the 3rd hidden card. So
it's a 1-1 function.
Right, so it has to be a 1-1 function.
But it doesn't have to be onto, because there might be, out of these 42, you're only going to use 35 of them. So there's
Right.
7 of these pairs that don't get used, which gives us a lot of flexibility here. It might be onto.
Yeah, it might be onto.
Not in this case, but with 8
Yeah.
it might be
Right.
onto.
Yeah, with 124 choose 5, it's got to be onto.
Right.
Yeah.
And in fact, a strategy is bad whenever it's not 1-1.
Right.
Whenever there's 2 ways to go backwards, because then I get my ordered collection, I don't know which way to go back.
Right. So okay, so who wants to be the spokesperson for the class? What should we use for the strategy for 1, 2, 3? Which card?
I did it just like choosing the first thing that comes to mind, 1, 2,
Okay.
and then looking for a place to put 2, 1 in.
Okay.
And just following that algorithm.
That means that you hide 3 and you show
1
Yeah,
and
show
2.
1 and 2. And now if you put 2, 1 in the next place, it fits. And now you got a new one. Like
Okay,
5.
so now we can't use 1, 2, or 2, 1 here, so let's try 2, 5. And we hide 1. Okay, so now you would go ahead and find the next possible place that you could fit 5 to?
Yeah.
Oh, gee.
That worked for me.
Huh.
That's good.
Huh.
So like the 2, 3,
So
5
here-
would be 5, 2.
Right. Wow, so Chris's method was to now go up to 2, 3, 5 and put the 5, 2 here because that's the next possible spot that we could fit that we could choose a 5 and a 2 out. So here we'd put 5, 2, and hide the 3. Great, so 1, 2, 6, I guess you would do.
I would have gone 1, 5 and then 1, 6, but. anything
Oh,
anything
you.
not to work.
Oh, I see. I see. So it seems like there's a lot of leeway here. I mean, let's just sort of go blindly through. So let's say 2, 6 means 1, 2, 7 means 1.
Yeah, let's just do as many as we can do until we're stuck. Or practice if you got the entire row. Who's the duplicate checker? Well, you're definitely not going to get any duplicates there, right? Because you're going to use the next.
Okay,
All right.
so we're okay now. Here with 2, 3, 4, let's see. So we've already done
3, 4 is taken.
3, 4 is taken. 2, 3 is not taken. Use 4, 3?
You can use.
Oh, okay, so let's use 4, 3. Okay, so for 2, 3, 6, let's see, 2, 3 is not taken, so let's use that. Now for 2, 3, 7, 2, 3 is taken, 3, 2 is not taken, so let's use that. Okay, so for 2, 4, 5, 2, 4 is taken? No, it's not. Good, let's use 2, 4. For 2, 4, 6, 4, 2 is not taken. Let's use 4, 2. Okay, so now for 2, 4, 7, let's see. 2, 4 is taken and 4, 2 is taken. 2, 7 is taken, but 4, 7, and 4, 7 is taken. But 2, 7 is taken, but 7, 2 is not taken, and neither is 7, 4. So let's use 7, 2. Okay, so now for 2, 5, 6, let's see. 2, 5 and 2, 6 are both taken. 5, 6 is taken. 5, 2 is not taken. 5, 2 is taken? Oh, geez. 5, 2 is taken. Okay, so 6, 5 is not taken.
Your computer may vary.
Okay, so 2, 5, 7. Let's see. 2, 5 is taken. 2, 7 is taken.
5, 7 is taken.
5, 7 is taken. 2,
7, 5.
7, 5 is not taken. Now finally for 2, 6, 7, let's see. 2, 6, 2, 7, and 6, 7. 7, 6, is that taken?
No.
No, okay, with 7, 6.
Okay, so now we go to our third row. 3, 4, 5. Let's see. 3, 4, 3, 5 are taken. 4, 5 is taken. 5, 4, is that taken? No. I'm going to be really shocked if this works. 3, 4, 6. So let's see. 3, 4 is taken. 3, 6 is taken. 4, 6 is taken. 6, 4 is taken? No. Three, 4, 7. 7, 3. 7, 3 is not taken. 3, 5, 6. 3, 5, and 3, 6 are taken. 5, 6 is taken. 6, 3 is not taken. Good. 3, 5, and 7, let's see. 5, 3 is not taken.
7, 3 is all right.
7, 3 is all right? 7, 3 is...
About
Right, 7, 3 is taken. 5, 3 is okay.
no,
5, 3 is not okay?
I don't think so.
Where's 5, 3? 5, 3 is not there.
3 is okay.
Okay, now 3, 6, 7. Let's see. 6, 3 is taken. 7, 3 is taken. How about 7, 6? That's taken too. And so are 3, 6, and 3, 7, and 6, 7. So now we're stuck. So we'd have to go back. Yeah.
Fill out the others, and then we'll only have 1 or 2 maybe that aren't.
If you win,
Yeah, I mean, that's what we could do. We could go through and continue. I mean, we're only 4 away. Let's sort of forget this one for right now.
Vậy bukan just change. don't you change this 6, 7 to 1, 6?
Oh, 1, 6 wasn't taken. Yeah, okay.
Because we don't have that 1 statement, so now we start to 6.
Okay, so I put 1,
But
6.
let me stop for a second before you go on. So Gadora's idea is fine because she's a human being and she's thinking. But if you're gonna
Right. I mean, the problem is you can't tell your computer to, well, if it screws up, then just go back and find. I mean,
you could, but you'd have to really program carefully. I mean,
Right.
You'd have to write a good program that knows what the best one is to kind of switch instead of just kind of looking at it intuitively and saying, oh, well, I can see that would be 3 and it would help me here. And if you're going to have your computer just go back to the last case and try the next possibility instead of the one and just backtrack, the worst case that happens, let's say none of these strategies work. Let's say we're actually really dead here. Then the worst thing that happens is you run through every single strategy in your backtracking and you finally report none of them work. And if you do that for this 3, 7 case, even this is centuries, right, if we try every strategy here. So we have to hope to get lucky in doing this the brute force way. And we have to hope that we don't have to backtrack hardly at all. And if we do, it's just very briefly. And there's a million different ways to write your program because none of them really work. Right? I mean, you're just hoping
Sorry.
for a lucky break here. So this is really an engineering kind of experiment rather than an algorithm to solve this thing.
I mean, I guess the answer is that at least I don't know and Shai doesn't know for what values there are solutions. I mean, so this is really some open-ended question. It's hard. Well, maybe it's not hard, but it seems hard to us.
With the pairs?
Pardon?
If you enumerate starting with the pairs, you say, okay, I can have a pair of 1, 2. What does that go to?
Mm-hmm.
I can have 2,
You
1.
need to go the other direction.
Yeah.
Right, to make your dictionary the other direction.
That might be a more clever way of generating.
That might be easier. Yeah, so Heather's suggesting, why don't you start with the pairs and generate your
It's gonna be a
triples that way?
one-way function anyway.
Right.
The foreground background doesn't matter.
Right.
That's a good idea.
Exactly.
Well, let's try to finish this.
Yeah,
up.
so let's try and finish this. Okay, so we took away 6, 7, so now we can put 6, 7 here. Okay, so 4, 5, 6. Let's see.
You can do the same thing with 1, 4, 6.
Yeah, okay. So now I want to put 4, 6 here. Okay, 4, 5, 7. Are any of those not taken? Probably not.
1, 5, 7. We can do the same thing.
Okay, so
7, 4 still open.
7, 4 still open?
We can use it in the next one, so you're going to have to...
Okay,
do one.
so
If we fix this,
so let's see. Let's change this to 1, 5, meaning 7, and then we can still use 5, 7.
And the next one we can use 7, 4. Is that
4, 7.
Yep.
well, 4, 7 we used. I think we used
7, 4.
Now finally for 5, 6, 7, let's see, we should be able to change it with 1, 5, 6. Oops, to use 1, 6, I guess?
We've used 1.
We've used 1, 6. 6, 1. Oh, 6, 1. Right. And now we can use 5, 6 here. Okay, so great. There's a strategy for this that works. Yeah, right. Memorize
it
this.
and do the trick, right?
The question is there, well, my question is, Shai's question is, how often can you find a strategy? Is it possible to find a strategy that works? Is it possible to find a nice way of enumerating a strategy? My question is, how many strategies are there? I mean, what's the probability that we just brute force hit upon a strategy when we just go through? I mean, the total number of strategies is this. How many of them are good? So I guess you could figure that out. I mean, that's harder.
When I assigned you to go ahead and run a program that could conceivably run for, 40,000 centuries, I don't expect you to run the program and wait. What I'm hoping is that when you have 52 cards and you're trying to, say, get it to work for 60, instead of 52, that so many of the strategies that you pick will work that if you just go ahead and enumerate them in any kind of an order, you're going to get really lucky and not have to look through even the teeniest fraction of this huge intractable universe, just because what Tara said, if you just pick one at random, you'd probably get lucky. Like, it'd be interesting to just pick a strategy completely at random and do it a million times and calculate what's the chance of you getting one, and probably the chance of you getting one is pretty good. So just pick one at random and try it, which is basically what I want you to try to do. So hopefully we can get some answers and see how high we can go. So you want to talk about Sham's wife's?
Yeah,
What's your
so
wife's name, Sham? We have to give her some credit.
Rajni.
Rajni?
Rajni?
R-A-J-N-I.
Rajni?
You're an N.
J. R-A-J-N-I.
Rajni. Okay, so Sham's wife Rajni came up with right. It's really nice. So she has a nice strategy, which is essentially it says.
And she'll be getting credit for this assignment.
So her strategy is for each, if you're given this set of 3 that you want to code, that you want to encode, first write down all the permutations in reverse lexicographic order. So that means, well, fortunately I have letters. That means, okay, first we write down CBA, then CAB, then, let's see, BCA, BAC, then ACB, ABC. So this is sort of the reverse dictionary order.
So lexicographic is a multisyllabic version of alphabetical.
And I guess the alphabet for 1, 2, 3, 4, 5, 6, 7, 8, 9 is just 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so first write down all the n factorial permutations of your guy, and then try to encode using this, right?
Yeah.
So try to hide go through your permutations in this order and try to hide the first one and show the second 2, and see if that works. See if that's already been hit by see if the second 2 has already been shown by your strategy before or not. And if it has been, then move on to the next one and try and use AB to encode C, and then try and use CA to encode B, and so forth.
I'm a little bit confused though. The first one, the CBA, that is clearly reverse lexicographic order. But the CAB, how?
So what I've done is I've written down the 6 permutations in reverse dictionary order. And
Well,
so
the first one's, I see what you're talking about, but how are you saying that CAB is reverse dictionary order?
they're not internally reverse order. If I have 6 words, namely CBA, CAB, BCA, BAC, ACB, and ABC. And in the dictionary, they would occur in the order ABC, ACB, BAC, BCA, CAB, CBA.
Okay.
And so then I
You compare
turn
the
that
2
upside
words,
down.
not the letters within
Right.
the word.
Okay. Okay.
Yeah. So Kabaz first.
Kabaz first. So Rajni, is that right? Rajni?
Rajni, yeah.
So the Rajni conjecture is that if you do this, you always get one that works before you get to the end of your list of 6. In other words, you never have to backtrack with this idea. And maybe we should do it on this list of 7 to see how it comes up with. But Shama's tried her suggestion, and so far you've never had to backtrack, right? If there was one, you found it. Is that true?
Yeah. And I've gone up to the deck of 27, choose 4, which is the highest for
4 cards.
4 cards, and it's worked up to then.
Right. So this found a strategy without backtracking for the maximum you could hope for choosing 4 cards. And now,
So now the question is, what happens for
how
5
far
cards?
Can we go with 5?
I mean, can it?
Or
Can
with 6 or with n?
right?
Like, what if we could prove that her way of generating always got a strategy that worked without backtracking? If we could prove that, then it would be a real algorithm. It wouldn't just be lucky. It would be a constructive kind of an algorithm. And we know that you could always get the maximum value or upper bound. And this problem would be solved, and nobody would ever look at it again. But I think that's really kind of a lot to hope for to prove that. I think we're just kind of lucky so far. And it'd be neat to see why it's really working. But nobody knows. So look at it. Try to see why it's working.
So let's do
her method and see that we don't get a backtrack. I hope.
So we would be coding the first letter of the tree each time.
Yeah. This one means A, B, encoding C. This one means CA encoding B. This one means AC encoding B. This means CB encoding A. And BC encoding A.
Why is it in reverse alphabetical order? Why not alphabetical order?
So the reason Shyam's wife, the reason Rajni, I think, chose reverse lexicographic order is that this...
conjecture because we can't ask her.
Right, I mean, she's not here. Well, if this distance learning were working, maybe we could dial her up and ask her. I mean,
it's a hologram.
Right. The idea is that here in this first column, we really want to use a lot of the ones. I mean, earlier when well, of course, in the strategy I just erased, we had to backtrack, and we tried to use a lot of the things that had 1, like we would use a 1, we wanted ones to occur a lot here because there's no ones over here. And so we want to use up the pairs that have ones in the first column. And so this sort of maximizes that. This uses the ABs and the A's a lot first. And so, you know, using the reverse lexicographic order has something to do with the fact that we've written down our numbers here in lexicographic order.
But I mean, if you do it the opposite way, you use up all the C's first.
Right, but there's a lot more C's over here. Well, there's a lot more 5, 6, 7s over here, and a lot more 1s over here. So really, we'd like to use the fact that there's 1s over here, rather than just sort of go blindly along.
Well, I'm saying just do it alphabetical order. Just flip it.
Sure, you could do that, and then start at the end, and that would work just as well.
Okay.
If both of them are in lexicographic order, what we found was you have a most inefficient strategy.
Right.
Right, that's about the worst thing.
Right.
You're right,
That's the
because
worst
very
thing you can
quickly you end up hiding combinations of 2 3s and 2 5s. The minute you hide 3 sets of them, then you automatically guarantee that there's 2 ways to go back to a 1. Right? I mean, did I say that right? I'm not sure I said that.
Yeah. So the problem is if we put both of these in lexicographic order, in alphabetical order, then what's going to happen is we're going to hide 1 an awful lot over here, and we're going to show an awful lot of 2 3s, 2 4s, 4 2s, 4 5s. And then when we get over here to something that has a 2, 4, and 5 in it, we're going to have already used up all the possibilities. And so we would have to backtrack. So it just turns out, you know, no one's proved anything yet. We haven't proven that this is the most efficient way to do it, but in the examples that Shyam has seen, this seems to be the nice way to do it.
So it works for all 3-card hands and 4-card hands, all the way to the
Wow.
Could we prove that there's only one strategy that works for 3 cards out of 8? And since this and show that this finds it?
Well, that would be nice, yeah,
Okay.
if we could do that. So Todd suggested, why don't we just prove that there's only one possible strategy for the maximal size deck? And if we could do that, and Shyam's strategy works, then we'd have an even nicer theorem. Yeah, but I don't think we're any closer to proving that than we are in proving anything.
Get right on that. Oh, I ran out of paper.
The margin is too small to contend.
Okay, so if we start with 1, 2, 3, the first thing is going to be CBA. Well, and that works because we haven't run out of anything yet. So we encode 2, 1 encodes 3. Does everyone see how I got that? So now I come to 4, 2, 1, and I want 4, 2, 1 is the first thing, but I've already used 2, 1. So I next come to 4, 1, 2. So I use 1, 2 to encode 4.
So you should realize it's not that you get it on the very first shot. Sometimes you have to go to the second, the third. Sometimes you'll even go down to the 6th one before you succeed. But you never go through all 6 possible pairs
And run out.
and run out. At least that's what the conjecture says. The conjecture doesn't say you get it on your very first shot. It says that you'll get it on one of your first 6 tries for each one of these triples. And then if you fail, there's no way to do it at all without having to backtrack and try some other one that you didn't try last time. It really knocks the number of possibilities down. What does it knock it down to?
Yeah, so if we use this strategy,
Well,
so
n factorial, the thing you just erased, the n factorial to the d to choose n. That's the old upper one.
okay, so that's the total number of strategies, n factorial to the d choose n. If we look at the total number of strategies there are using this algorithm, well, at each of the n choose,
Be n times n factorial.
It'll be n choose, at each of the d choose n
You have n
guys, you have n
factorial.
factorial things to look at.
No, it's much less. But you never
No.
backtrack here.
It's D choose
You don't
n times
backtrack.
n
Yeah, it's d
factorial.
choose n times n factorial.
Because you only go through it once, and you only try the n factorial one time through. So if you fail, you don't go back and try all the other combinations.
EJ doesn't look convinced.
Okay.
So is anyone else not convinced?
He's not convinced.
So
what number would this give us for the one that we computed earlier with the total
It
strategies?
would be
we had,
6
like-
times 56 rather than 6 to the 56th.
Yeah.
Right.
So what number would this give us?
With the calculator, so we could just compare it.
Wait, small. You have a hard time even coming up with a fraction of what that.
that's like Carl Sagan. As many stars as there are in the
Let's even say
Yeah.
2,000. Let's say 10,000.
right. 6 times 56, 300 plus 36.
But you should realize that that gets us out of the crazy universe into something reasonable for this case of 3 and a deck of 7. But you very quickly go back into the twilight zone the minute n gets up to.
Right. I mean, the minute n gets up to 5 or 6. I mean, the point is we still have an n factorial there, right? I mean, checking all these strategies is still not the smartest way to go, because n factorial, we know that's n to the n, and this is d choose n times n factorial, and so this still is not going to be. Checking all these slick strategies is still not going to be an efficient way to solve this problem. It may be the best way that we know of right now, but it's not efficient. So.
But it's just 200 million. It's the work of mere moments.
Right. Right. But still, if you
2.5 million hands per
Right.
to card deck and
Right.
and factorials.
I guess what is this for 124 and 5? What's 124 choose 5 times 5 factorial? Anyone?
It would be 124 times 123.
Yeah.
121 and 120.
Anyone have a computer or a calculator rather?
What do you want to know?
124 times 123 times 122 times 121. No, that cancels out this, right?
Yeah, because that's just the permutations of 124 things taken 5.
Right. Right. Oh, do I have to multiply by 100? Times 120. Wait, whoa. 2701 800. This is the number of things we have to check for 124 cards, choose 5. So the number of slick strategies is a lot. Yeah, 27 trillion. That's not so bad. 27. Yeah, 27 trillion.
27 trillion.
No, billion. Billion. 27 billion. That's not so bad. That's 27 seconds, according to Shai's.
Nanosecond.
Yeah. So, okay. Anyway, let's finish filling this out. So we can't choose 2, 1 or 1, 2 here, so we choose 2, 5? No.
No, I think 5, 1.
5, 1. And here I guess we choose 6, 1.
Wouldn't it be 1, 3 following 3, 1?
Oops. Oh, yeah, I forgot the 1, 3.
We can let. Why don't you good enough to do it?
Right. So, in any event, you could do this. I mean, you could sit here and do this if you were not as tired as I am, maybe. Yeah. Are there any questions about how the strategy works? Or how, I mean, what the strategy is? I mean, why does it work? If you can answer why it works, then great. You know, you can prove our conjecture, maybe.
Anybody else offered a strategy?
That's the only strategy. Does anyone else have a strategy?
Chris
Yeah, the
offered a
strategy,
strategy at the beginning.
Oh, yeah.
Yeah, it worked.
Does your strategy backtrack?
Not in the ways that I've tried it so far.
Okay, so-
so I haven't tried it as extensively as Sean.
So your strategy was actually not to go in reverse order. You actually go in forward order. But anytime you get one, you look for a place where the flip can be used.
To generalize my algorithm, it would be to list all of the ordered pairs and drop the ordered pairs in the first place they fit.
Right.
That's what you were thinking.
And that's more or less what Heather was thinking, yeah.
Right.
Yeah.
Things if we have more ordered
Yeah,
pairs.
list the ordered pairs and put
Right.
them in the first place where they belong.
Right.
And then if it's already filled, go to the next possible place.
Right.
Yeah.
And if that never gets up to a situation where you can't put one in and you have to pick them all up and start again, then you get the same result as Sean.
Right.
You'll always find
Right.
So
That seems like a good strategy too. So our second strategy is look at all the ordered pairs.
Hey, does it come up with the same thing?
I don't know. I was just going to write that down and figure it out.
What if they're the same?
Once again,
Slick what? Slick strategy 2 is to list all order pairs. And I guess we list them in lexicographic order. Right, the first two would start backwards. They're not going to be the same strategy.
Oh, well, so here's something else. So if it actually does work, if you don't get a backtrack, then we know there's not a unique strategy.
Right,
So one way or the other, you win. That's the best kind of math, right? You can conjectures.
right, right. Yeah, so they're definitely not going to be the same strategies because these strategies, I guess we list all the ordered pairs in lexicographic order, right? We list 1, 2,
Right.
2, 1, 1, 3, 3, 1.
it would be 1, 2, 1, 3, 1, 5.
What? Oh, you list them that way. You don't even do this 1, 2, 1, 3.
No, but
Oh, yeah.
when you do 1, 2, do you also throw 2, 1 in also? I thought that was the implication of the
Well,
strategy.
that's how I did it when I did it by hand, and I think that is analogous to doing it this way. I'd have to think about it some more to make sure that that's the case.
Yeah, I'm not sure that it
If you do it
is.
this way, I don't think it's going to be the same because if you do 1, 2, and 1, 3, well, maybe it is. I don't know. I have to think about it.
So here we get 1, 2. Here we get 1, 3, 1, 4.
We still get to stick a 1, 7 in anyway.
What? Oh.
So we can stick a 1, 7 in.
Even in a case where there's 8, even when it's exactly enough information? I'm not sure you can.
Yeah, I don't know. This doesn't...
It's already generating different answers.
Yeah, I mean, this is very different from Sham's. So...
The way I'm doing it,
Mhm.
it's just switch the 2 digits.
Oh, okay.
That's what I'm getting.
So, but maybe that gives us 2 different strategies. In fact, if you have a strategy, then you can reverse all your pairs and you'll still have another strategy, right?
Yeah, right.
Oh, okay.
So
fine.
there's at least 2 strategies.
2, right.
Yeah.
But, all right, so we want to
So-
call those in the same equivalency class,
Right.
right?
Exactly. So yeah, if we have an equivalence
That's what
relation,
equivalency class
an
is.
equivalence relation in this case would be flip all pairs.
Right. The minute you have 2 things that you start feeling are the same, then you just
Oh.
want to think of them as unique. So you call them all in the same equivalency class.
In fact, so if you have a strategy for n cards out of a d card deck, then you're going to have another equivalence relation, namely use the same permutation to permute your strategy all the way along, and that's going to give you a new strategy. And so we have an equivalence class. Again, we have an equivalence relation where 2 strategies are equivalent if you can use the same permutation to permute all the answers, all the dictionary entries, or whatever you want to call them. So, you look confused. Should I say that again? So, so one thing we've just noticed is that switching all pairs gives a new strategy. And we want these to be the same.
So the size of the equivalency class is going to be n minus 1 factorial?
Yeah, that's right. So in general, if we have this as our thing that we want to encode, and so what we do is we say A, B, C, D, E, and we encode this to be F. So we have, now we're choosing 1, 2, 3, 4, 5, 6 cards. If we choose a permutation of 5 cards, so fix one permutation, then if we apply that permutation, so if, say our permutation is switch the first 2, then if we switch the first 2 of each of our 5-card entries in our dictionary, then that's going to be a different strategy. It's going to be, somehow we want to call that equivalent to the first one. And so applying this to each 5-card subset gives a new strategy. And again, these should be equivalent.
So in what case are you working here? What size deck? And
So any size deck, choose 6 cards.
any size choose 6?
Yeah. In general, it will be if we choose n cards, fix a permutation of n minus 1 cards, blah, 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 blah. This will give a new permutation of each, or this will give a new strategy, and we should call these equivalent. So in this case, we'll get equivalence classes of strategies. The equivalence classes will be the n minus 1 factorial permutations applied to some given strategy. We can probably, well, we'd have to somehow choose one of them to be the least, but we don't even want to think about that. Okay. So maybe there is one equivalence class of strategies. Maybe there's who knows how many.
Of successful strategies.
Right, of successful strategies. Yeah.
And maybe it depends on how big the deck is.
Right.
Maybe when it's the maximum size, you have one equivalence class.
Right. I mean, I guess the hope is that when you have the maximal size deck, there's one equivalence class of good strategies. But that's even not clear to me. I sort of suspect that they're...
You would expect there to be more than one equivalence class when you don't have a maximum.
Right.
There's just too much flexibility.
I think my gut instinct is that when you have the maximal size set, there should just be one equivalence class of strategies.
That would make it a nice problem.
Yeah. But that would make it a nice paper, right?
Yeah, right.
Right. So.
This idea of doing it in this backwards way it just feels like just the right interleave, right?
Yeah. Yeah. So this is nice. The moral of today's recitation, I guess, is that this is hard. I mean, this is sort of unknown. Like, we don't know what the answer is. And so, this is what math is sort of about. This is what research in any field is sort of about. You have some question, you don't know the answer, and you just plug away, and you program your computer to test a few cases, and you say, oh, look, this strategy seems to work. Now let's prove it. And, of course, then you have no idea how you're supposed to prove it. But that's the moral of the story.
It makes it more fun.
So, are there any questions? Any answers? I guess we can stop